All right, so that's why we want to use induction generators. Then if you look at some, again, there's a review of something you have all seen before, right? It's a rotor with a stator, and you have 3 windings. Right? So we have, so to remind ourselves, this is a rotor, that's the rotating part. Stator, that's the stationary part. And then we have different windings. Right? So these are the rotor windings. And these are the stator windings. Okay, so this is a good design where things are simple, right? So none of this changes dynamically in real time. You put this in, and this is it. Okay. Unlike a synchronous generator, you have exciter, you have permanent magnet, you have current, all that. This you don't need any of that. Okay, so this is a very simple design. You put the windings together, and if you have a magnetic field in the air gap, this thing will turn. So that's the design we have. So again, most of this just a reminder, right, for us. I'm assuming most of you have seen this before, so just a little bit reminder how induction generator works. So a magnetic field is, right? So induction motor turns by inducing magnetic field. So we always will be talking about 3-phase generators and 3-phase motors. There is not a all induction generators are 3-phase. There's no non-3-phase induction generators out there. Okay, so when you have 3 phases, right? So we have a phase A, we have phase B, that's with the offset. We have phase C with another offset. So this is our 3 phases. And when we have different phases, they induce a magnetic field, and we turn this magnetic field. So we have so 3 different phases. You put them together. If you in the phasor rotation, what happens is we have 3 phasors. That's 120 degrees apart. Okay, so 120 degrees apart, and you put it inside the stator. Then what happens is you have this kind of magnetic field. Okay, so this is different phase. Each phase induces a vector in space, and then we see the sum of the vectors. So this is the 3-phase design. Okay. So if we have this kind of field, then what happens is the magnetic field will turn. So sinusoids, since we have AC power, so as you vary the AC power, as you vary the AC sine curves, you have a turning magnetic field. So once we have a turning magnetic field, what happens is the rotor has to turn. So the stator has a turning field, and then the rotor will have so the rotor turns as well, responding to this turning magnetic field. Okay, so again, just to recall that because this is 3-phase and all phases are balanced, this rotating field will have constant magnitude and constant frequency. Okay, so that's one reason we use 3-phase, right? We do not have a difference when this thing turns. All phases are equal. So once it turns, it will turn at a constant frequency, constant magnitude. Okay, so this will turn, and will turn at some frequency. So in an induction generator or induction motor, where does these fields come from? Are they generated by the motor or generated by the grid? Who's generating this turning magnetic field? Let's say a wind turbine, you have wind coming in one side, connecting to the grid. So is the wind generating this rotating field, or is the grid generating this rotating field? Okay. the grid, right? So the grid is always generating these constant frequency rotating fields. Okay, so one thing to keep, you have to always keep in mind is for an induction generator to work, somebody needs to give you this constant field. Okay, somebody needs to give you this turning magnetic field. The generator does not provide this turning magnetic field. The generator, when the motor responds to this, but something else has to give us a reference field that turns at some constant frequency. Okay, so often you'll see, why can't we use a type 1 wind turbine directly powering a load? Because something has to set the frequency. Okay, so the generator itself does not do that. So something else is doing that. Right, so that's why we can talk about this field as a constant frequency. Right. So wind does not blow at constant speed. The blade certainly does not turn at a constant frequency. But since this is maintained by the grid, a good assumption is that this is 60 hertz. Yeah, that turns out constant frequency. Okay. So the speed of this air gap field, air gap flux between the rotor and the stator, this is one revolution per one AC cycle. And so again, if you have this is the stator, this is the rotor, you have something here that's your constant turns out, one revolution per AC cycle. So since our AC cycle has a very fixed frequency, right? So the time per AC cycle, this is 1 over the frequency. So 1 over 60 hertz, so it's relatively fast turning, very fast frequency. And then the speed of the flux is typically measured in RPM. Okay, so this is typically measuring RPM, revolutions per minute, not per second. It's just a more common unit you see in machines. Okay, gives slightly better looking numbers if you talk about per minute rather than per second. Okay. So you see something like 3600 RPM, which are just 60 hertz. Okay, so but more common unit is RPM. So normally when we see the speed, this is called an S. This is 60 times the synchronous frequency. This gives us RPM, or something called revolutions per minute. Okay, right. So this is just the speed of the air gap flux. This is maintained by the grid. So this NS, this is called the synchronous speed. Okay, because this is external speed generated by the grid for us. Any questions after this one? Okay, so if you look at the outside field at 60 hertz, then the synchronous speed is 3600 RPM. Is this a fast or slow speed? Think of the gear from the gearbox perspective. This is very fast from a gearbox perspective, right? So if you have a typical turbine, the blades, as it turns at 30 RPM. Now if I had to match the synchronous speed, I have to match it at 3600 RPM. Okay, so that's not a design, that makes your gearbox life not very simple. Okay, so that makes your life pretty complicated. So the synchronous speed sometimes is too high to use. It just turns too fast. I don't want to convert a mechanical torque that's at low RPM to a mechanical torque of RPM this high. So how do we slow down the speed, the synchronous speed of the induction generator? There are ways to slow this down. I say I want to make the gearbox life a bit easier, not to convert it to 3600. Remember from 351? How do you lower the speed?
Increase the rotor number, the poles of the rotor.
Right. Yeah, so in Zoom, right? So this correct, increase the number of poles. Right. So the idea is increase the number of poles. So this speed is the absolute, or this is the max speed you can have for a synchronous generator, for a induction generator. It's not going to go faster than this speed, but can go slower. And the way for it to go slower is just to artificially make the field seem slower. Just increase the number of poles, makes the external AC cycle seem slower than the actual is. Okay? So that's why you can step down the poles. Okay? So for example, this is a design of a 4-pole machine, right? 2-pole pairs. What this does is before you have so one AC cycle, you repeat after one AC cycle. But here, because you have 2 A phases, so if you look at the A phase, you have 2 of them. So because you have 2 of them, it takes 2 rotations for things to become periodic. Right? It just takes 2 turns for things to be periodic. So this, so you have 4 poles. Okay, so it takes 2 rotations of the AC field to be periodic. It just you turn slower. So first rotation, you go from this A phase to this A phase. Next rotation, you come back to this A phase. So just basically this makes the AC field as if it's going at half the speed. Right? So number of poles is important, right? So we have, so each phase has 1 coil, right? Has a single coil. So to spell this out a bit more, this is called a 2-pole machine. Then what we see is rotor moves 360 degrees per AC cycle. Right? So you can reduce this down by each phase. So just adding a coil. This gives us a 4-pole machine. Then the rotor moves 180. Okay, so you have a slower rotor. The rotor spins, synchronous speed appears as if the AC cycle is going slow. Okay. Any questions to this? All right. So okay. So then we have a simple. So there's question. The coil is added on the stator. Right? Yeah. So you add the pairs of coils on. You add pairs of coils. Yeah. So they're evenly spaced out. So everything is still symmetrical. So when I say you have 2 coils, not an arbitrary on the rotor, right? So they have to be all evenly spaced. They have to be added in this way. They have to all match up. They have to be added this way. Okay, so you add coils and you add number of poles, basically, you add more wires into it. And then that gives us a simple way of computing. That gives us a simple way of computing the synchronous speed. Basically, you take your 60 times Fs, 60 times Fs, you divide by the number of pole pairs you have. Okay. So the slightly confusing terminology, which is something's hard to avoid. There's a difference between something called a pole pair and something called a pole, right? So if you have one phase, let's say IA this way, right? So this is because for every phase you have a current that comes in and current that comes out, A prime. This is called this is 1 pole pair. This is 2 poles. Okay, so standard, if you don't add any additional poles, you have 2 poles or 1 pole pair. And so if you add something, for example, this is a 4-pole machine. It's 4 poles. Okay. So the equation becomes 60 times Fs divided by pole pair, so 120 times Fs divided by the number of poles. Just depending on, and often the terminology we have the number of poles. Okay, so you cannot, the machine with the smallest number of poles is a 2-pole machine. Then you go 2, 4, 6, 8, and so on. Okay? That's why number of poles can only be even integers. Okay, you cannot have, for example, a 5-pole machine. That's not possible. Okay, so you have even integers, right? Okay, and the trade-off between the number of poles you have and the gearboxes, the more poles you add, so the simpler the gearbox becomes, because you don't have to step up the speed in the gearbox anymore. But then you eventually run out of room on the rotor to add poles. You're limited by physical space of how many poles you can. You need space. You need put wires in the rotor and stator, so you run out of space. Right, so it's not often a trade-off of how many poles can you put it in. So normally you get something like 6 or 8 poles. Okay, so the synchronous speed is much lower, right? Much lower than before, but still not quite at the speed the blades will be turning. So you still need a gearbox, but this makes the gearbox not, you don't have to step up the speed all that much in the gearbox. Okay, so you have 6 or 8 poles. Any more, it's just, physically hard to manufacture that. Okay. Any other questions? Okay, so number of poles is important in induction machines. That's physically Tesla's idea. So all this goes back to Tesla. We had this idea how to build a motor and how to change the speed by adding number of poles. All right, so that's that changes the synchronous frequency. So the way the motor works is, again, the simple review is basically Faraday's law. Right? What Faraday's law says, if you put voltage across conductor, then the conductor will move. Right? There's a force exerted on conductor. So the way to think about it is E is some voltage on a conductor. Okay, so I want to put a voltage on this conductor. So how does this voltage happen? Right? If I have a conductor, how do I induce a voltage onto it? Well, idea is if this conductor is in a magnetic field, right? So this B is some flux density. And V is now the speed. Okay. So Faraday's law says that so L is the length of how long this conductor is. So Faraday's law says if you have a piece of conductor that's in a magnetic field, you move this thing, that will generate a voltage. That generates some voltage thing across the conductor. And then if you generate this voltage, right? So if you're moving this thing around and you're generating this voltage, well, it's a conductor, so it has to give you a current. Okay, that's just Faraday's law. So F is the force, I is the current. Okay? So you take a piece of conductor in a field. If you move relative to the field, you feel a voltage and you generate some current. That's just a linear version of Faraday's law. And then for our motors and machines and generators, it's just a rotational version of Faraday's law. Okay, instead of talking about V, speed, we talk about rotation. Right? Instead of talking about force, we talk about torque. So we have from linear motion, this is linear motion. This gets converted to a rotational motion. So you still take some conductor. Now imagine this conductor is turning in a magnetic field. If you turn, you have some voltage, some function of delta n. So delta n is a relative difference in speed. Right, so if our external field is turning at ns at some synchronous frequency, If you turn at a different frequency, then you generate some voltage. And because this is a you generate this voltage, again, this is conductor, you feel current and torque. Okay, you generate some torque. So this is angular momentum or angular motion. Okay, so the trick is Faraday's equation. Faraday's law is something that's very standard. And really, after we had electric machines and motors, then people start writing down this rotating frame of reference for Faraday's law. Okay, just a different reference, the same exact intuition works. Okay. So the way the motor rotates is you basically apply a three-phase to the stator. You have a field that rotates. Okay. If you have a speed difference, right? So now you have a rotating stator. You have a rotating field. If the rotor is stationary, the rotor sees a rotating field, will try to catch up. Right? The rotor will turn because there's a speed difference between the conductors on the rotor and the outside field. So the rotor turns, and that's how torque is generated. Torque turns the mechanical part of the rotor. Okay. So when you start a rotor, for sure, if you start a rotor from standstill and you apply the outside field, the rotor will turn. And what that rotor does is try to catch up to a synchronous speed. The rotor does is always try to catch up to the speed of the field. Right? So the rotor will, so the motor tries to catch up to NS. Okay, so if it's not rotating, then we'll try to rotate NS. And what happens? Why does it want to be at NS? Well, so if delta N equal to 0, right? So if the motor speed equals to NS, equal to the synchronous speed of the outside field, then relative to the motion of the outside magnetic field, there's no speed difference. There's no speed difference. There's no torque. The torque is 0. Okay, and you stay at the speed. Okay? You stay at synchronous speed. Right? So if you have no speed difference, then you stay at synchronous speed because there's no torque being generated. Right? So that's again, very simple idea. Okay? So how do you generate how do you generate power, or how do you consume power to supply a load? Basically, all it boils down to you have some speed difference. Right? So speed difference will give you a non-zero torque, and that will lead to either a power produced or power being consumed, power being produced. Okay, so all this is so if the speed of the motor is not equal to the synchronous speed, there will be some torque. Some net torque on the rotor. So this will basically speed up or slow down the rotor. So try this torque, there'll be a torque on the motor. So this is so then the rotor can either supply a load or generate power. Okay. So whether it actually is consuming or generating power depending on the sign of this difference, right? Depending whether you're faster or slower than the synchronous speed. But if there is a speed difference, some net power will be exchanged between the outside grid and maintaining synchronous frequency and the rotor. Okay? There are some power exchange if the speed is not the same as the synchronous speed, whichever way the power exchange goes, depending on the sign of this difference. All right, so then this gives us the equation of, again, says really what we want to look at is the difference in speed, really is the difference in speed. And this is a function of the torque of the load, right? If I'm supplying load. or this is a function of torque of the generation. Okay, so I'm either generating or consuming power. All this depends on the speed difference. So this whole thing is try to again reinforce the idea is looking at the speed itself does not really have much meaning. We really want to look at it as the speed difference, not the absolute speed by itself. Okay. So knowing a motor is spinning at some absolute speed is not terribly useful. Right? We want to know what the speed difference is. Okay. So this comes down back to, so based on the speed difference, we can define something called slip. Right? Because what happens is often is again, we can look at the speed difference, but often the equation works out by if you want to normalize the speed difference by the synchronicity. Okay, so the equation works out, there's a normalization factor. Okay, so this is called slip. There's many, all these definitions are equivalent. You can do this in radians per second if you want. All these are equivalent definitions for slip. They're the same equation. And just recall that in radians per second, this is omega is n over 60. Okay, so n is RPM for most of us. Most of the times, then omega is in radians per second. Okay, so this is slip. So this is the standard notation. Again, review. I'm assuming we have all things slip before. Okay, so just review of where the slip comes from and definition of slip. All right, so we have slip. Now let's look at the motor again drawing this. Again, always in the air gap, right? So because you're connected to the external grid, because the stator is connected to the grid, so it's always a synchronous frequency in the air gap. Your rotor is connected to the turbine and the gearbox, so this rotates at some speed. Right? And the idea is basically setting up a circuit diagram. Okay? So what we want to do is, here what I have is this kind of picture, right? This kind of picture, they rotate at different speed. What we want is we want an equation relating the speed difference to something like power. At the end of the day, what I want is I want an equation that goes from S to power. Okay, so that's the end of the day. I want that equation. Having this for intuition is good, but when we do computations, we want the equation to come out. Okay, so I'm going to show you basically the way to think about it. I'll show you some of the complexities in deriving this equation. Actually, it's not a trivial matter to derive this equation. Things get complicated actually rather fast once you draw the circuit diagram. Okay, so we're not going to really talk about how we solve the complication in this class. I'll get you there. And the notes will contain the nice math that makes things work out. Okay, so if you look, things start to get a bit complicated, just keep that in mind. We'll have a simple equation at the end of the day. We will get to a circuit diagram that you have all seen before, for example, 351. Just in 351, I sort of said, okay, this is the circuit. Here, I'll show a little bit how do you get to that circuit. Okay, what's going on inside the machine? Right, so I want the circuit, right? To get an equation, I need a circuit diagram, and from that circuit diagram, I want to compute the voltage and current to get power. So into a circuit, what does this look like? Okay, well, from a circuit theory perspective, what does a rotating induction machine look like? What a rotating induction machine looks like is basically 6 inductors rotating against each other. What you have is you have 3 inductors, those are the coils on the stator. You have another 3 inductors, those are the coils on the rotor, they're rotating against each other. And there's this coupling among the inductors that we'll care about. It will care about how they're coupled together to each other. That basically give us a current being generated and voltage being generated. Okay. So, right, so think about this, right? So the first thing when you think about this kind of machine is you have to pick a frame of reference. And everything's rotating against each other. So the easiest way is to think of, okay, my frame of reference is the rotor speed. Right? Let's fix the rotor as a frame. So everything is rotating against this. Take the stator phase A on the stator as a frame of reference. Everything is rotating against this. The rotor is rotating. Have some angle difference against it. Okay? So this is rotating at some speed. Okay, omega s, let's say, or omega. What did I do? Oh, okay. All right, so I'm rotating at some speed. Then this rotor is rotating at some other speed. Let's say omega 2. Okay, it's rotating at some other speed. And because there is a speed difference, so what happens if there's speed difference between two things that's rotating? There'll be a torque, but think of in terms of this variable. So if I have two rotations that have a slight speed difference, what happens is you create an angle between them. The idea is we'll create some angle. Right? There is a torque making the rotor rotate. But then what happens is really you create this angle called theta 2. Okay, this angle depending on the different speed of rotation at each pass. Okay. So because this angle depends on speed rotation, then different angles create slightly different circuits, will create different spacing between the inductors. Okay, because different angles, inductors are at different distance from each other. Okay, so that's why the inductance change in this circuit. I have a different rotation speed, I have a different angle, and things change. Okay? So putting this into a circuit, what we have is you can think of this kind of circuit diagram. We have three inductors on each side, three inducting on each side. They're all coupled together. And the different couplings between the inductors changes as the angle changes. Okay, that's the important part. In a transformer, what we have is we also have two stationary sides. In the transformer, the primary and secondary are stationary. They're not moving. There's coils on a core, around a core. Here, what we have is we do have this kind of transformer setup, but then because things are rotating right, at different speed, then the coupling between the inductor changes. And the coupling between inductor changes. So what happens when you study this kind of things is there are three inductors on each side, right? Three on each side. Now, how many couplings are there? Right? What are the number of different numbers of relationships we have? There are 3 by 3, 9 different couplings. Because each inductor can couple on one side, will couple to any of the 3 on the other side. There's actually 9 numbers you have to keep track of. Okay, so again, this is because things are moving. This is right. So things are not stationary. Okay. So at the end of the day, what you have is you have this L called inductances. So inductances are no longer numbers. It's a matrix describing how things relate to each other. Okay, so this is a huge matrix describing how things relate to each other. And basically, you can think of there's 9 coupling across the sides. And then internally to each other, they can also couple. Okay, so let me be clear. So there are 3 on each side. So if you look at how inductor 1, so let's look at how 1 works. So how do we describe basically the current or the magnetic field going through inductor 1? There are 6 relationships actually. So there's 1 to 1, how do I relate to myself? This is more trivial. 1 to 2, 1 to 3, less trivial. 1 to 4, 1 to 5, and 1 to 6. Okay, so 4, 5, 6 are even less trivial. Okay, so there are 6 numbers I have to track of for induction 1. How does induction 1 work with the others? Okay, so if you look at this, this is most naturally describing a matrix. And what this matrix does is if all these inductors, okay, so these things are turning. I want to describe as this angle changes. What is, for example, the mutual inductance between these two? There are two inductors that couple in some way. There's a magnetic couple. I want to describe how all these things are related to each other. I want to make that description. So this problem was written down in the 1920s. People were trying to solve this problem. Right? So at that time, if you see a 6 by 6 matrix, really your life will be not very easy. Okay, so now, at least numerically you can deal with this matrix. But at that time, you have a 6 by 6 matrix. The question is, what do you do with this matrix? Okay, there's a lot of numbers in this matrix. I don't really want to describe how this matrix changes across time. Okay, so things seem very complicated in this matrix. Okay. So the idea is, so any ideas how you want to deal with this matrix? Let's say you were doing this exercise in the early 1920s. You realize there's just 6 inductors going around. And somebody wrote down this matrix for you and say, okay, to get a circuit, deal with this matrix. Right. Right. So the suggestion in class is, okay, can we set some to 0? Can I get a number to look at? Unfortunately, no. There's nothing that small in this matrix. There's nothing that small in this matrix. Okay, so we're not going to do the math. Doing the math will take us 2 classes. None of you guys will beat after 2 classes. But think of some of the intuition or some things that will help you deal with the 6 by 6. Right? So think about what are the simplifying things I have. Right? So it's 6 by 6. But are there symmetries in this matrix? Can I explore symmetry? Well, what is the number 1 symmetry we explore in 3-phase circuits? When we deal with 3-phase, we always boil down to a single phase equivalent. We never write down the 3 by 3 matrix and deal with it, right? So the number 1 thing you try with this matrix is, okay, even though there's 36 numbers, everything's 3-phase. So maybe that will simplify things for you. Right? So that's a realization at that time. A, B, C, right? A1, B1, C1 are rotating at the same speed. They are different by a factor of 120 degrees. Similarly to this for A2, B2, and C2. Right? All these things are 3-phase. So nobody deal with this matrix. This L, simpler. How do you make it as this? Everything 3-phase. Okay, we have 3-phase circuit. So these numbers are not sort of arbitrary numbers that pops up. So we have 3-phase. So that knocks down a bunch of numbers. Basically, you don't have to deal with 6 by 6 anymore. Hopefully, you can replace this by sort of single phase equivalent. Second, there's symmetry in this circuit, right? The coupling from A2, for example, A1 to A2 is very related to the coupling from A2 to A1, right? These are symmetric things, there's symmetry, okay? So together between these two, what you can do is you can think of there is 3 orthogonal eigenvectors to L. Turns out, you can look, so you make all these assumptions, L will have very nice matrix properties. And then there are 3 orthogonal eigenvectors to L. They're all symmetric to each other. They're all equivalent to each other. So by using 3-phase, you can basically get this matrix to look at 3 single-phase systems going around. Okay. So even though everything is coupled and all that are complicated, there are 3 orthogonal eigenvectors. So there is a single phase equivalent. Okay, so that's basically where linear algebra comes in. Okay, so all you guys who learn linear algebra will think, where does eigenvectors, why does eigenvectors spanning subspace matter? Is actually used every time you use a motor. That's where it comes into use. Okay. So for people who taken power electronics, there will be this called something called a DQ0 string. There's something called Parkes transformation, if you have seen this. But again, we will not talk this about anymore in class. I'll upload slides that actually does a step-by-step calculation. Interesting. You'll see how the math all works out. Okay, you'll see how the math works out. They're quite, so it does not require very hard math, but they're quite useful calculation. Otherwise, we'll be dealing with this. Okay. Any questions about this? Different inductance? Okay, so just we will now deal with it. So we'll, basically you have all those things going on. Later, after class, we'll see how this are dealt, right? So what we do is we will take a single phase equivalent. Okay. So this is actually not just assuming numbers are there. This actually comes out because this matrix has a particular eigenvector structure. Okay, so there's not actually an assumption. This is not an assumption. This is a equivalent representation that you can take. I would just not go through why. This is the case. Okay, it takes too much time. It takes way too much time to go through that. Okay. Again, if you do power electronics, you'll see this again and again. In power electronics, you ever see the DQ free? This is basically the D free in the DQ0 free. Okay. So if you, I don't know where you guys got to that yet, but this is just a frame of reference you can look at. Okay. So single circuit equivalent of a motor turns out to come out to be very simple. Yeah. So our single phase equivalent is tremendously simple. So this is saying that you have A1, right? You have some voltage at A1. You have some stator. On the stator, you have some resistance. On the stator, you have, this is your winding here. You may have a shunt inductance. This is another winding here. And then we have a resistor on the secondary side. This is V. Okay, so this is just a transformer circuit. Right? It's just a transformer circuit we've been looking at. This is an induction motor circuit that you have seen before. Okay, so and these are R1, X1, X2 prime, R2 prime over S, VA2 prime over S. Okay, so this is just the basic circuit we had before. So what this captures basically captures the relationship between one pair of inductors. Okay. And every other pairs of inductors all look exactly the same as this one. So that's why it's called a single phase equivalent. Right. So this will represent the entire motor circuit for us. Okay. All right, so this is if it is a motor, then the way power flows is power will flow in this direction. So you have power flow in this direction. And then if you're a motor, what happens is S is omega S minus omega over omega S. This is bigger than 0. Okay? So that's why it's a motor. You have net power. So for power flows left to right. So because you're right, so way to understand this is you're rotating at slower than synchronous speed. So the outside field keeps trying pulling you up the synchronous speed. To do that, it needs to inject some torque, give you more torque for you to spin faster. So whether that torque comes from, that torque comes from the power of the grid. That's where the torque comes from. Okay. That's what S is positive. So that's our equivalent circuit. Then for a generator, for a generator, then this is same circuit, drawn exactly the same circuit, except the power flows the other way. The power flows out this way. So for a generator, all we have is same machine run backwards. So power flows right to left. So here, S equals omega S minus omega over omega S. This is negative. Right? So what happens is you're spinning faster than the external field. You're spinning faster than the field. So the field tries to slow you down. Okay, so it has to take out some torque that's in the rotor. Right, so it takes out this torque. Where does this torque go? It goes into the grid as tau being generated. Okay, so all the equations from both circuits are exactly the same. It's just when you're plugging S into one of them, it has a negative sign. Okay, for the motor, it has a negative sign. So sorry, for the generator, S has a negative sign. You need to be faster than synchronous speed. Okay. Any questions? Okay, so last thing just to remember that, here we have all this x1, x2 prime, all of these things. These are not these numbers. How they relate to this L1, L2, and so on, it's actually, you need to compute a relationship. Okay, so x1 here and x2 prime are not just the inductance on the wire themselves. So that's not the case. They capture all of this interaction into one term. Okay, so to compute these terms, you have to know the transform. There's some equation that compute these terms. Okay, so when you do questions, of course, we'll just give you the value of all the things. But again, to remember, that doesn't mean that's the actual value of the coil of the inductor. Okay, this captures all the different interactions, right? Okay, so now again, it's a good time to take our break. So take a 10-minute break. Then we'll get into equations for induction motor. Induction generator. Okay, so reminding you that voltage, current, and power equations here. Come back at 9:38. Okay, all right, so let's get started again. So we're just gonna look at write down the equations in more detail. So let's write it down for generators. Since we're working with generators this time, okay, so then you have a circuit, VA1. So the left-hand side will always be the grid in our notation. Okay, the one or the left-hand side will always be the grid. This is just how these things are drawn. Okay, so let's write down the voltages and the parameters. Let's compute the currents. Do some current voltage computation. Okay. So on the right-hand side, what we have is we have a voltage of VA2 prime over S. If the rotor side has some voltage, then this voltage gets raised up by 1 over S. This resistor, R2 prime, this will be, this resistor has a value of R2 prime over S, right? So again, that's where the slip comes in. So if you do the calculation, do the equations, that's where the slips comes in. So why is this a generator? Well, S is omega S minus omega divided by omega S. This is less than 0. Okay, so because S is less than 0, this is a negative resistance. This is a negative resistance. Of course, it doesn't, there's no negative resistance in the world, but from a modeling perspective, if you're faster than the synchronous speed, what looks like is your resistance is negative. So you can generate power. So the power generated comes out of this resistor. I have a negative S. You flow current, this generates power across resistor. So that's where the power comes from in the system. This is x2 prime. This is x1, r1, xn. Right, so this is our full circuit. Then there's various different ways we can write down different voltage and current relationship between them. Right? So let's say, because we are writing down a generator circuit, so let's say current flows from right to left. Just a little bit pictorially depicting that we're sending power from, current from right to left. So we're sending power from right to left. Okay. So then we can write down all the equation for different currents. So let's end off this. IM. So IA1, this is minus. All right, so how much power? Sorry, I'll write down this one. So VA1, how much voltage is there? Well, this is minus R1 IA1 minus JX1 IA1. All right, so the voltage we get is JXM IM. Right, so the voltage by Kirchhoff's voltage law, you get the voltage at the grid is described by this equation. So of course, often the way it works is you know VA1 and you're solving for the current. Okay, so this equation normally works by knowing VA1 solving the current. But we can write the voltage to current equations. Similarly, we can write the VA2 equations. This is V2 over S on the right-hand side. This is R2 prime over S times IA2 prime plus JX2 prime IA2 prime. Okay. All right, so these are equations. So I'll, there are typed up version in the notes later because you can read the handwriting. But here, just I want to go through them just to remind you where they come from. It's from basic circuit equations. Look at the voltage and current. The important thing to remember for this equation, these are all complex numbers. Okay, we're dealing with the circuit with inductors, with complex voltages, the angles that have different angles. So important to remember that VI are phasors now, are complex numbers. Okay. So sometimes, when you're doing the computation, you tend to forget these are complex numbers. Then the numbers will be way off. If you don't include the complex, you don't include J, things like that, numbers will be way off. So just remember, these are complex circuits. So these are complex number calculations. Okay, so that's the thing to remember. Otherwise, it's looking up an equation, looking up some equation we have. All right, so this is, okay, so generator. So the one thing that's a little bit special in this circuit is the developed resistance. Okay? So if you look at the circuit on the secondary side, we have something called R2 prime over S. And so where does this R2 prime over S come? So how do we think about this? And so there's two parts in R2 prime over S. There's R2 prime, which is the physical resistance you have in the wire. There's this 1 over S idea. 1 over S is the fact that you have a slip. You have some slip in the circuit. So the best way to think of this resistor is think of this one. You can always write R2 prime over S as R2 prime plus something called RD. This is always possible. And then RD has a following equation, R2 prime S, 1 minus S. So we often conceptually think of the circuit as R2 prime plus RD, and RD is called developed resistance. Okay, so the way it's called developed resistance is you can think of R2 prime is always there. Right? R2 prime is physically in the circuit. That does not change. Then because you have a slip, some resistance gets added to the circuit. Some resistance gets added to the circuit. You have a slip, you have a torque that adds resistance to the circuit. And the part that's added is RD. Right? Just R2 prime over S times 1 minus S. So that's conceptually a way to think about what the generator is doing. Okay, the generator, by spinning faster than the synchronous frequency, is adding a negative resistor to the circuit. Okay, it's appearing as a source, but it's not appearing as a voltage or current source, right, which is different than standard circuit. It's appearing as a negative resistor at outside source. Okay, so normally people think about generator, you think of a generator as a voltage source or current source or voltage control current, all the kind of things. Here it's natural to think of the generator as an added resistance, a negative resistance, but added resistance. Okay, so that's where the generator comes in. And also, it does not, so this generator does not generate reactive power. Okay, that's another way to see it. It's just a resistor. So the generator does not generate reactive power at all. Okay, it just generates some active power, and the reactive power is whatever the inductors work out to be. Okay, but all your generator doing is adding another resistor to the circuit to generate some active power out of it. Any questions? Go ahead. Yeah. Yeah, right. So yeah, so the question is, where does the prime come from? Prime comes from the secondary side of a transformer. Yeah, so because this is not an actual transformer, it's an induction machine, we'll never talk about the actual transformer ratio or this kind of thing. So all the secondary side will be the prime numbers. Okay, so if things are a little bit inconsistent, just think of this just one circuit. Yeah. So this RD, for example, sometimes it has prime, sometimes not. And you'll find there's different books and papers have different conventions. So with a prime, because there is a transformer, and this transformer comes from when you deal with this 6x6 matrix, there's a factor that comes out. There's a complex transformer factor that comes out. But we never, in practice, we never deal with the transforming ratio. Right? So yeah, so the prime comes from transformer. It's okay if this is a little bit inconsistent in your note. So this is not a notation we'll pick up. Where we'll not pick this notation. Okay, because the transformer ratio is never explicit anyways. Okay, this is okay. Any other questions? Okay, so we have a developed resistance, right? This is developed by slip being negative. And then the calculation is actually quite easy once you get to the circuit. Okay, you compute your speed, you compute a synchronous speed, you get a slip. And you shove into all these kind of equations to compute the voltage and current, and you can compute the power. Okay, so the mechanical, so the cranking this equation through is fairly simple to do. Right. Okay, so these slides just repeat the equations we have, right? In case the handwriting is hard to read, but we're just going to repeat the equations here. So during a homework, during exam, I know where to find the equations. Okay, so since the exams are open book and open everything, the main trick is knowing where the equations are and not spending a lot of time finding equations. Okay, that's where the main thing is. Okay. Once you know the equations, once you know where the equations are, is plug them in and check it through. Okay, check the equations. Right. Okay, so this is our type 1. Again, this is why it's simple. when you look at these equations, nowhere does the fact this is in a wind turbine come. Okay, nowhere does this come. Because who's doing the hard work is the gearbox that's doing the hard work. The gearbox is making sure your slip is, you have a good slip. Once that is determined, then your generator does not care the fact that it is in a wind turbine. Just generate power that way. Okay, and so that's why it's simple, and why it's, we're not expecting this thing to perform very well, okay, as a generator. But this is the first step. Then as we develop more, type 2 and type 3, you start seeing the fact that it matters as in a wind turbine. That fact will start to matter. Currently, it does not matter as in a wind turbine. It's a gearbox that deciding the frequency, the slip, and then we go from there. Okay. All right, so the best way is to use this equation, just do an example. Just sort of, going through all the equations so we can possibly see. Okay. All right, so and this is also introduces the different terminologies you're likely to see if you read the book or you read some other reference material. Okay. And again, when you look at this circuit, the main thing is this circuit is actually typically very complicated. Doing this without a computer program gets a very long calculation. Okay, so this question actually has a lot of words that basically saying what you can ignore in this circuit. Okay, so that's the way it's developed. So the circuit is correct, but often we ignore a bunch of things in the circuit. Okay, so let's just go through and read what this problem says. Okay, so it gives you what x1 is, x2 is, xm is, r1 is, r2 is. All these are standard parameters we have in here. That's the turn ratio of the generator is 1, meaning don't worry about the transformer. So we also assume the turn ratio of the generator is 1. So we're not going to worry that the transformer. The slip is negative 0.1, right? So that means you're generating your negative slip. You're connected to a 690 volt grid. The resistance of the core is very high. So what this means is you can just ignore the fact that you have this shunt inductor there. This shunt inductor makes the calculation complicated and doesn't change the numbers all that much. And normally this is a very high number anyway. So we're going to assume that's the open circuit and ignore it. Okay. So we can approximate this and just ignore it. And then compute the following things. Compute the reactive power to the generator, the developed power, the power to the grid, and the power factor of the generator terminal. Okay. All right, so let's look at all these and remind ourselves what these all mean. We have all seen this terminologies for induction machines, at least before. Who remembers what developed power is? Right, so there's something called developed power. So let's go through and remind ourselves what all these things mean. Okay, so okay, so let's compute all of this and do computations, and all this will come back to you what these things mean. Okay. So let's compute the first reactive power of the generator. Let's compute this reactive power. Okay, so what does reactive power do? Okay. So we're going to ignore the center branch. We're going to ignore this branch. So what do we have is we have some grid that's fixed. R2, S1 over S, R2, X2, X1, R1. Okay. So I want to compute, what is the reactive power? How much reactive power do we have in this grid? Okay. All right, so to compute reactive power, one thing we can do is to first compute the current and look at the current flow through each of the inductors. Right, so the only thing that's consuming reactive power in this grid, is the two inductors, X1, X2 we have. So we know the current, we can figure out how much power they consume. Okay. Right, so recall that this is, so what we can do is, right, so the Q is 3 times IA squared x1 plus x2, right? So here we have our Q equation with respect to the computing reactive power. So where does the 3 come from? Anyone remember? Where the 3? Right. Right. So 3 comes from the fact that this is 3-phase, right? So again, all the 3 and root 3 will come back into this equation. Okay, so then they never go away in this kind of calculation. So this 690 volts, what voltage is this? Right, since we're talking about this 3-phase now. Is this a single phase voltage or what is this?
A 3-phase RMS problem.
Right, this is a line-to-line 3-phase voltage. This is line-to-line voltage. Okay, so this is line-to-line. Okay, so when you see this kind of voltage given without saying what it is, it's always line-to-line. It's always line-to-line, if we don't say what it is. Okay? So to convert it to a single phase, to the per phase voltage, this is 360 over root 3. Right? So this root 3 comes back again into our equations, because you will still be doing line-to-line and per phase convergence in this. Right? So just again, when you read the equations, remember where root 3 goes, where 3 goes. That is, again, right? So again, most in the midterm, most of the answer, if it's wrong, it's off by a factor. Okay, just remember, check your calculation. Remember this. Okay, so IA we can compute, right? We can compute IA. This is this V over, right? You have a voltage, VA1, over the fact that you have different resistances and reactances. Okay, so this is I, right? So remember in the phasor calculation, I is V over R1 plus R2 plus RD plus J X1 plus X2. Okay, so to get the magnitude of the current, we just square. Right? So to get the magnitude, we have a square root at the bottom. Okay, you plug this in. This is roughly 41 amps. Okay. Right. Any questions with the current calculation? Yeah. Right. So the current comes from voltage divided by the total impedance I have in the grid, which is R1 plus R2 plus RD. And then the total reactance I have is X1 plus X2. So together we get the current equation in phasor form, then we can get the magnitude, right, taking square root. All right, so this is our current equation. So our reactive power is Q this 3IA squared X1 plus X2. Plugging these numbers, we get 65 kilowatt. All right, so for this reactive power, is this reactive power positive or negative? Is it delivered by the generator or consumed by the generator? Okay.
Consumed, right?
Right.
Because you have a bunch of inductors, but it only supplies active.
Right. So this is always consumed by the generator. Right? Again, the generator is a negative resistance that does not provide reactive power. Okay, but then these inductors consume reactive power because current flows through it. So this is supplied by the grid. Okay, so this generator does not supply reactive power. The grid has to supply reactive power for this generator to work. So that's again why you cannot directly, for example, just even if your load somehow can maintain a frequency, it doesn't. Sometimes you cannot directly connect direct to the load. Something has to provide this reactive power. And so here we're going to assuming it's coming out of this VA1, so coming out of this grid. Okay? Okay, so let's look at the developed power. Okay, let's look at developed power. So PD in this case, let's compute the developed power. Then this is the power that's given out by this negative resistor. Developed power means I'm a generator, all right? So I'm a negative resistor as a generator, then this is power coming out of this. So developed power, basically you have this R2S 1 over S. That's how much power this resistor is generating for us. Okay. So it's a power generated by this resistor. So let's compute the power generated by this. Well, this is again just a resistor, so this is completely active power. 3IA squared R2S 1 minus S. So this is the current flowing through it is IA. Square that, multiply by this resistance, you got the power generated. Okay, so this is again 3 times 41 squared. R2 is 1 minus 0.1. So this is where the minus slip, negative slip comes in. 1 plus 0.1. This is about minus 56 kilowatts. Okay. So this minus sign again corresponds to the fact that the slip is negative. Okay, so this minus sign tells you, so the power is generated by RD, by this resistor. I have a minus sign. Okay. So normally the power across resistor has to be positive. In this case, because the slip is negative, I have some generated power here. Right. Questions about this calculation? So again, the computations here are not tricky. Just you have to know what you're computing. You have to know for what number you're computing. And then boils down to basic circuit analysis. Okay. So this is the power generated by the grid, by the generator. So then how much power is delivered to the grid? How do we compute that? All right, so this is my power generated. What about power delivered? To the grid.
We'll include also the power losses.
Right. So this is just, you take this generated power, subtract the power you lose on R1 and R2. Right. That will be the power delivered to the grid. So the power out to the grid is the power you generated. Right? Subtract 3 times IA R1 plus R2. Right? So you lose power in R1. So if you look at the circuit diagram, you lose power in this guy. So then subtract that gives you the total power coming to the grid. This is about 46 kilowatts. Okay. So we do lose some power. So we get. Then the last thing is power factor. Okay. So we know Q, we know P. Right. So we know Q and P. So this is just power factor is cosine of the angle of Q over P. Power factor of 0.57 lagging. So you can, once you know P and Q, you know the power factor. Normally for this generator, we don't care about power factor all that much because you have no control of your power factor at all. There's not like a synchronous generator where you can decide your power factor by changing the PT, how much reactive power you generate. Here you have no control of this. Okay, so it is this sort of it is what it is. Like the computer power factor. It's not going to be great for most type 1 or type 2 generators, but that's not something you can control through the generator. Okay. Any questions for this example?
It's just general question. Then
Yeah.
how can we compensate this? How can we enhance the power factor in this case?
Right. So the question is, how do you enhance or how do you compensate for such a poor power factor? The short answer is for type 1, you don't. Okay, so the grid has to compensate for it. Or something else in the grid has to deal with this. Okay, so for more advanced types, there are different ways to do it. For example, you can add a capacitor to this, right? You can add a variable capacitor to boost up the reactive power. That normally is very costly because if you think of a big wind farm, then there'll be a lot of reactive power consumed by the generators. And typically our capacitors are not that large. Large capacitors are not super reliable. Okay, so we don't want to add very, very large capacitors to the grid. So that's you do see capacitive compensation, but sometimes it's not cost efficient. So we really deal with this when we get to type 3. We really deal with this when we get to type 3. What type 3 does is you can inject, so you can think of this as following how to deal with it. If I can inject a current that doesn't touch active power, but somehow it's sort of anti-phase to the reactive power part, can I just inject this current with the right phase to cancel out the reactive power? Okay, so that's the idea in type 3. And we'll see that design. So type 3 has that design. Basically, it gives you another path for current to flow, and this current tries to cancel out this reactive power. Okay? For type 1, type 2, for this kind of induction generator, not much you can do that. And so that's why people was not hugely successful in the early versions of this wind turbines. It's just hard to use. It can generate active power. Just the grid has to do a lot of things for it to work. When you want a generator, you want the generator to do this type of thing, not the other things in the grid to do everything for you. Okay, so this is the early version, right? So reactive power is definitely a huge drawback of why they were not very popular. But we'll see later. So type 3 is really the one that deals with reactive power well. Any other questions?
I've got a quick question. So
Sure.
in the original model drawing, we had a voltage source on the right-hand side,
Right.
V2 prime over S. Can you explain why that's not included here?
Right, okay, so good. So here I have this VA2 prime over S. This is if you have some voltage at the rotor. So you have exciter in the rotor, or you can maintain a voltage in the rotor. In most problems for type 1, we don't have external voltage source we have access to in the rotor. So that's just 0. That VA2 prime is 0 for type 1 and type 2. Right, so if we had a voltage source, it will get amplified by 1 over S. Right, but we don't have this voltage source. Right now, we haven't done how to add this voltage source yet. Okay. All right. Okay. So yeah. So that's a good question actually. So that's why later again for type 3 we'll start using that voltage source, because this 1 over S is actually typically a big number. So if you can somehow get a little bit voltage or current into there, this actually gets a lot of boost. The 1 over S will boost it up. Okay? So there's a good. So this, if we have voltage there, we can use it. But at least for type 1, we don't have a way to add voltage yet. Right, so good questions. Any other questions? Okay, all right. So that's one example. Let's do one more example that puts everything together. Why not? Okay, so this goes from, how large a turbine is, all the way to, what different kind of losses we have on total system efficiency. Okay, so just putting all the equation we have seen together. So we have a wind turbine that's 25 meters long blades, upwind speed of 50 meters per second, coefficient performance 30%. This is a 6-pole machine. The mechanical efficiency of the turbine 85%, electrical efficiency of the generator is 90%. Compute a bunch of stuff. Okay, so this is how all the equations come together. You go from the mechanical power to the electric power being generated. So let's do that. Let's compute everything. Let's compute that. So let's say let's compute the power captured by the blade. So this is power in wind half delta A E cubed multiplied by CP, right? So again, if the equation doesn't say, assume delta is 1, right? The density of air is 1. So I'll put everything in. This is half times 1 times 20 pi 25 squared, 15 cubed times 0.3. Okay, so all this come together, you can compute the power in the captured by the blade. With this coefficient performance, this gives you 3.3 megawatts. Okay, so this is the mechanical power we get. Let's see at the end of the day how much power we get out as we generate. So next, compute the slip. So the speed is 1 RPM. Okay, right. 1260 RPM. Let's compute the synchronous speed. So the synchronous speed is given by 120, the frequency divided by number of poles. Frequency is 60, number of poles is 6. This is 6-pole machine. So this is RPM. Okay. So the slip is NS minus N over NS. This is negative 0.05, right? Okay, any questions? Okay, so this is our slip. So, right, so, okay, so 0.3, this should be 993 kilowatts. Sorry, did the computation there. So the power capture is 993 kilowatts. Then this is, the slip is negative 0.05. So normally slip is a small number, the absolute value, right? So it's 0.05, negative 0.1, this kind of number. Okay, so let's say look at the power delivered to the stator of the blade. So power delivered to the stator, this is what we have. Right, so this is the hour power that we get in wind times the mechanical efficiency. So we have the mechanical efficiency is 85%. Right, so we have 85% efficiency here. So this, for example, represent the gearbox losses we're having in the system. Right, so we lose something in the gearbox, we lose something in the okay, so now we can compute the, so this is our power to the stator. So now let's compute the air gap power. Let's compute the output electric power. So we get power to the stator. Let's see how much power we get at the end of the day. So the alpha power. Right, so this alpha power is with this partial stator, how much do we get out of it? Right? How much power do we get out of it? So let's do that. Actually, do we have enough? Actually, now looking at this, I want to do this next class. Because I'm not sure you guys remember the equation how we use going from stator side power to air gap power, Steve power. Yeah, so we covered that before in induction motors. I'm not sure anybody remembers that. Okay, so let's actually stop this example here. Next time we'll do a little bit review on different relationship between all kind of different powers in the motor. Then we'll pick up again from this example. Okay, so we'll stop here today. Next class we'll pick up from there. Then we'll redo this example because there's quite a number of equations that is useful for you guys to know. Okay, and also I want to give you a place to find them. Okay, so we'll stop here today, do that, continue next time. So again, this is just saying if you're ever interested in how do you get this matrix to something reasonably looking, the rest of the slides go through that. Okay, so this will not be on the exam, this will not be on homework questions, will not be on the end. But if you're interested, take a look at these different transformations. Okay, right, so then see you guys on Thursday.
Thank you.